Hello and good afternoon, everyone. Thank you all for being here today. My name is Bautista Quilora. I'm a student at UCEMA. Rightfully so, we would like to thank UCEMA and the UCEMA Finance Club for organizing this event. Most importantly, I would like to thank our guest speakers who have been kind enough to share their valuable time with us this afternoon. Today's talk, Estimations of Default Probabilities for Low Default Portfolios, is brought to us by Gustavo Serenelli and Emiliano Delfau. Gustavo works as a partner in the Finance Services Division, specializing in risk management. With more than 17 years of consulting experience, he has amassed a plethora of knowledge in commodities, industries of mass consumption, and the financial sector. As for Emiliano, he is Chief Risk Officer at Open Bank Argentina, where he brings 18 years of experience in business, finance, and consulting across both Argentina and Latin America. This talk will cover techniques for estimating default probabilities and rating calibration for low default portfolios. To this end, techniques for constructing non-informative prior distributions will be introduced for the application in Bayesian estimates of these parameters. This talk is estimated to be an hour long. Please hold your questions till the end, and also feel free to send them through the chat. And now, I'll give them a warm welcome, Gustavo and Emiliano.
Okay, thank you very much, Bautista. Gustavo, in order to begin the journey, can you give to us a rough overview of the paper, please?
Yes. Emiliano, I will tell you, or I will tell the audience, more or less the story or the history behind this paper. I think it would be a good insight of two things. What is the direct consequence of this paper, but also what is the indirect consequence or the indirect goal of this consequence of this paper? Because perhaps the indirect goal of this paper is at least as important as the direct goal of this paper. So telling you guys the story of this paper, I think it would be a good insight regarding that. I remember I was attending a client, a financial entity in 2010, 2012, something like that, regarding an operational risk engagement. We had to measure the frequency, the yearly frequency of their operational risk. So we were performing some interviews to our client, and we were having more or less the following conversation. Okay, this operational risk in particular, I don't know, mistakes in some procedure, which is the yearly frequency of this operational risk. Well, it's zero. No, it can't be zero. Yes, it's zero, because it never happened. I have been working in this bank during 10 years, and it never happened to me. Okay, but that never happened. That doesn't mean that it won't happen never. Okay, you're right. What do we do? So I started thinking, and I said, okay, if in 10 years, let's say in 10 trials, it never happened, it would be weird if we say that the probability of occurrence of this event is 10%. Because if the probability would be 10%, if the probability would have been 10%, then we would have seen by now, in 10 years, one event. And so 10% sounds a little weird. It should be lower than 10%. But also we said that 0% sounds pretty optimistic. So it should be something in the middle between 0% and 10%. If we calculate some kind of average among all the scenarios of all the probability scenarios between 0% and 10%, we will reach to something in the middle. For example, 5%. Okay, we shook hands and we liked the methodology. We applied several times more. We could measure those operational risks that had never happened. A couple of years later, I took the responsibility also of helping the auditors of my firm in their audit of financial statements regarding things related to quantitative finance. I don't know, expected losses for credit risk, actuarial reserves for insurance, and in many cases, again, I have to provide a number in cases where the event we were measuring never happened, have never happened. So, well, I naturally try to apply this intuition. Okay, we have to measure the credit risk allowance for a portfolio. This portfolio in the past, we have had 10 exposures. Those 10 exposures never incurred in a default situation. So we, in a way, we have 10 trials, 0 default, that should give us 0% probability of default. However, applying the intuition explained before, we can say, okay, it should be higher than 0%, it should be lower than 10%. Something in the middle is that 5% that I mentioned before. But then when I try to apply this rationale in an auditing engagement, I found that I should be more rigorous regarding the formalization of this line of reasoning, because when you are auditing, you have to justify everything with much more rigor. You have to be sure that your decision is objective, is agnostic. So I try to develop the math in order to prove that this line of reasoning is agnostic, is objective in any sense. I was reaching to some results, but it was being hard, and I did something more intelligent. I Googled. And when I Googled, I found that there were some guys that have already thought about it before me and have already solved the problem. These guys were Shannon, Sheffield, Bernardo, that in the second half of the 20th century have tackled this problem and have already solved. These guys, what they have done is take what is called Bayes analysis. Bayes analysis, in Spanish, Bayes is pronounced Bayes. B-A-Y-E-S. Bayes analysis. The statistical methodology developed in the 1900s that talks about prior probabilities and such. Many, I'm sure, pretty all the audience have studied Bayes analysis and Bayes method in their statistic courses. But this Bayes method found some kind of rebirth during the second half of the 20th century. And these guys, Shannon, Jeffrey, and Bernardo, using this rebirth of this Bayes analysis, found the solution, the objective diagnostic solution of this problem of estimating a probability, a non-zero probability, when they are in front of events that never happened in the past. And what they found is that the exact answer to our problem is very similar to the intuition I explained before. If we go back to the example we talked before, we had in the past 10 trials, I don't know, 10 years of an exposure, for example, for credit with 10 trials. Our n, our variable n, the trials is 10, and it never happened. So our x, the events that we found in the past are 0. So the naive estimation of the probability is 0/10. However, we propose not working with 0%, but working with 5%. 5% is not 0/10, it's 0.5/10. What the result obtained by this guy, Shannon, Jeffrey, and Bernardo, is pretty similar to this 0.5/10. What they found is that the objective diagnostic answer is not 0.5/10, but 0.5/10 plus 1. So putting it in a formula, it is 0.5/n plus 1.
Okay, thank you.
So these guys developed some kind of rebirth of the Bayesian method. What did they do exactly? Let me show you a couple of slides that I think would be pretty clear. Let me find a way to present. Okay. I guess you can see the presentation.
Yes. Perfect.
So we were talking about this example. We have 0 credit risk default in 10 historical loans. Here we are talking about credit risk, but we can apply this methodology to anything, any case, any situation in which we have 0 events or we have very little events. I don't know, actual losses, operational risk, expected losses for credit risk, economic capital calculation, whatever. Here we are talking about credit risk. We have a situation in which we have 10 historical loans and 0 credit risk default. The question was, which is the probability of default of our client? And we said in first place, okay, the naive answer is 0%. However, thinking about it a little more, we said, no, 5% is a nicer answer. It's some kind of average among all the values that range between 0% and 10%. And that 5% comes from calculating 0.5/10. 0.5/10, you reach to 5%. However, as I told you, the correct answer, the objective answer given by this guy, Jeffrey, Bernardo, Shannon, etc., is 0.5/11. How did they reach to this result? Okay, we said that this 5% that we were talking before is some kind of average of all the PD scenario, of all the probability of default scenario, all the PD scenarios that range between 0% and 10%. If we average all the numbers between 0% and 10%, we will reach to this 5% average. However, we can ask ourselves, do we have to weight this PD scenario by anything else? It looks like, yes, we have to weight this PD scenario by something else. I mean, if the PD, the real PD of this portfolio is 0%, then it would be, we would be sure that this portfolio would have produced in 10 trials 0 default. Because if the default probability is 0%, we will be sure that we will find after 10 trials 0 default. However, if the default probability is not 0%, but 10%, there will be a non-zero probability of finding more than 0 defaults in 10 trials. So we would not be that sure with a 10% probability that we would find zero defaults in 10 trials. So this likelihood looks like should have some weight in our average. So what these guys tried is to analyze the different scenarios, the different PD scenarios. I don't know, for example, 0% of probability of default, and for each of these scenarios, they calculated the likelihood of having 0 defaults in 10 trials. Okay, if we have a probability of default of 0%, it would be 100. We would be 100% sure that we won't find any default in 10 trials. Okay, perfect. However, if the probability of default is 1%, then the likelihood of finding 0 defaults in 10 trials would be something around 90%. Being not very rigorous, we can think, okay, if in one trial the default probability is 1%, in 10 trials, the probability of finding at least one default is 10 times the probability of finding one default in one trial. So it sounds reasonable that the likelihood of finding 0 defaults in 10 trials is 90%. And if we keep on performing this calculation, we will find that in the upper limit of our scenarios, we'll find that with a 10% probability of default, the likelihood of finding 0 defaults in 10 scenarios will be 35%. That 35% is merely a typical statistical calculation of the probability. That is to say, okay, if the PD is 10%, the probability of not incurring a default situation is 90%. If the probability of not incurring in a default situation in one trial is 90%, the probability of not incurring in a default situation in 10 trials is that 90% to the 10th power. That 90% to the 10th power is that 35% that we find there. So here we have the different PD scenarios, and for each of the PD scenarios, we have the likelihood of finding 0 defaults in 10 trials, given the PD of each scenario. So as I said before, it looks nice to perform some kind of weight of each scenario with this likelihood. We multiply each probability of default by each of these weights, and then we divide by the sum of each of these weights. So we perform the sum of all these multiplications. The arrow represent the multiplication of each PD by each of these likelihood. And in the denominator, we put the sum of each of these weights. As a consequence, we have our estimation of the probability of default. Okay, for all of the range that we define, each of the PD, we multiply it with each of the weights we define. We define the weights as the likelihood of finding zero default in 10 trials given that PD, and then we divide by the sum of those weights. Are we good up to now? Okay.
Perfect.
Okay. Then we can say, well, but why we should stop in the 10% scenario? If the 10% scenario has a non-zero likelihood of finding zero default in 10 trials, perhaps we should also weigh the 11% scenario. Okay, let's do it. If we have a probability of default of 11%, then the likelihood of finding zero defaults in 10 trials is 31%. That is to say, 89% to the 10th power. And then we can keep on doing it to each of the PD scenarios that we can work with. And we can follow this calculation up to the 99%. It would be really difficult to find zero defaults in 10 trials when the probability of default is 99%. But however, there is a non-zero likelihood of finding zero default in 10 trials. When you perform the calculation, it gives this ridiculous low number, but it is a non-zero number. So we can also take into account this scenario with this negligible weight, and we can continue all this calculation. So we have now our final calculation, our final estimation of the PD, having in mind this rationale of weighting all the PD scenarios with how likely is to find what we found, that we have zero defaults in 10 trials, given the PD that we are analyzing in each of the scenarios. When we perform this calculation, we have a bad news. The result is pretty ugly. The result is pretty ugly because when we perform this calculation for all the scenarios, we find that the result is 8.33% in this example. 8.33% is pretty close to the 10% limit that we say we didn't like, and it is pretty far from the 0% limit that we said it was pretty optimistic. And we would like to find something more close to the middle, more close to the middle point. And also, it is really close to the limit that we said it is less likely to find the default probability. Because if the default probability is 10%, the likelihood of finding zero default in 10 trials is 35%. It's pretty low. So we would be more satisfied if this average would have given us something more close to the middle or more closer to the lowest limit of our range of PD values. So we can think, okay, do we have to wait by something more? Do we have to wait by anything else? We have two possible answers here. Yes and no. But in fact, we don't have two possible answers. We have just one answer. Because no is equal to yes. I mean, if we don't weight by anything else, what we are doing is weighting by something else. We are weighting by 1. Here, in this calculation, when we stop weighting by anything else, what we did is weighting all the previous scenario also by 1. So the question should be, is weighting by 1 okay? Is it okay to weight all these scenarios by 1 and not by something else? And the answer that comes from our interior, from our soul, is yes, because 1 is agnostic, it's the uniform distribution. And we all think that the uniform distribution is a distribution that represents some kind of agnosticism, some kind of objectivity. What these guys have studied, have developed in the second half of the 20th century is that this uniform distribution is not objective. This uniform distribution is not agnostic. There is a distribution that is more objective. What they have studied, what they have created is some theory called information theory. They sort of quantify the information that certain object has. And for example, they quantify how much information a statistical distribution has. They develop some measure of information, entropy. They develop a distribution for this problem called Sheffield distribution. And what they found is that working with this other distribution that we are showing in this graph, this red distribution, this smile function, this function that has some sort of smile shape, is more agnostic, is more objective than working with the uniform distribution. This was for me like the gift that you see in the WhatsApp, the gift of the guy who have the formulas in the background and the fireworks.
Yeah.
This was for me a moment that really shook my mind. Okay, in what sense does this distribution is more agnostic, is more objective than the uniform distribution? And you started asking that, Emiliano. The
Yes.
idea there are two things that we are going to tackle in a couple of minutes. That this distribution is better than the uniform distribution. It does not depend on the parameterization of our problem, and it's the distribution that minimizes the subjective information that we introduce to the problem. We would tackle these two ideas in a couple of minutes. First, let me tell the audience what we did with the paper regarding this idea. When we found about all this line of reasoning, we said, okay, we should write something about this, because the practice that we have seen in the region and in the world regarding the estimation of default probabilities in low default scenario is varies a lot, it is not very clear what to do in this scenario. I have never seen anything written regarding what to do in a credit risk environment when we have 0 events of default. But it didn't sound good to write a paper saying, okay, in this scenario, look at the paper developed by Sheffield in 1946. Look at the paper developed by Bernardo in 1979. And in those papers, they solved the problem, and the answer is 0.5 over n plus 1. It was pretty poor to develop a paper stating simply that. So what we try to do is to find a problem in which a second derivative of this problem in which this idea could be helpful. And then we found the problem of calibrating a rating model. When we calibrate a rating model, what we have are different categories, different rating categories to which we have to assign a default probability. Okay, we have the AAA category. We have the AA category. We have the A category. We have the BBB category, the BB category, B category, CCC category, CC category, the C category, 9 categories in this example. And for all these examples, we have some samples. We have some trials, and we have some defaults. In low default portfolios, is pretty usual, it's pretty common to find that we have samples with some statistical error. And in those cases, it's pretty usual to find that perhaps the observed default rate of the AAA category is higher than, for example, the observed default rate of the AA category. And that is not economically sensible because the AAA category should represent a lower credit risk than the AA category. So what we ask is there a way to use this rebirth of this base method in order to provide an agnostic and objective calibration of these rating models? Is there a way to provide an agnostic and objective way of assigning default probability in order for them to comply with the hierarchy of the order that they have to obey? And what we found that we can apply this idea to this context where we have to assign probabilities to an ordered set of categories. So this is what we tackle in our paper. However, I think it is important to mention that the indirect consequence of our paper, that is to say, that the sole estimation of a default probability when we have 0 default is a problem that is already solved, and the solution is this formula that we find here, 0.5 over n plus 1. That is written in equation 10 of our paper. I think that that answer to that small problem, I think perhaps is at least as important as the direct goal of our paper. So this is the idea of our paper. Okay, answer the question of how to estimate a default probability when we have no default. we have to be honest, we didn't solve that problem. We just telling the finance community that it is already solved by these guys, Jeffrey, Bernardo, such. The answer is 0.5 over n plus 1 by some kind of agnosticism or objective measurement. And then we use this idea to solve the problem of calibrating a rating model and estimating probabilities where we have to assign them to an order set. Okay.
Okay.
So what I have to answer you, Emiliano, from the question you did is, okay, in what sense this Shepherd distribution is better in weighting this scenario? Okay, this is what we are going to tackle in the following two slides. Just to sum up this slide, what we find is that we don't weight this scenario by the uniform distribution by 1. But if we weight this scenario by this Shepherd distribution, by this smile function, what we find is that the probability that we estimate is not that 8.3%, but this 0.5 over 11. That gives us something more or less 4.5%. It's pretty close to our 5% that the intuition told us in the beginning of our conversation. So in order to answer your question, Emiliano, in what sense this Shepherd distribution is better than the uniform distribution? The difficult part of your question is not in what sense this Shepherd distribution is better. The difficult part of your question is to liberate ourselves from the idea that the uniform distribution is agnostic.
Okay.
Because we feel it in our hearts, in our soul, that the uniform distribution is agnostic.
Yes, ex ante, no?
Yeah. So in what sense the uniform distribution is not agnostic? When we work with the uniform distribution, we are putting inside that decision our personal beliefs. This is again a moment. What do I mean? That we are putting in the problem our personal beliefs. I'm not going to be totally rigorous with my explanation because it doesn't fit in a 1-hour conversation, but please follow me with the idea. When we were taught about statistics, we learned that the fundamental object of study in statistics is the probability. In our case, the default probability. The fundament in every, I think that in every university of the world, what it is explained is that the fundamental object of study in statistics is the probability. So we tend to think that the probability should be uniform because it's the fundamental object of study. At least our statistics teachers told us that. What is the probability? I'm going to give a not rigorous answer, but please follow me with the idea. We can think that the probability, in our case, the default probability, is the thing that we introduce in the binomial distribution. Okay, if we want to measure the probability of finding X defaults in n trials with the probability of PD, what we have to calculate is PD to the X power times 1 minus PD to the n minus X power, all this time the binomial coefficient with n and x as parameters. The probability is the thing that we introduce in the binomial distribution. However, imagine from 1 minute that in Andromeda's galaxy there is a planet. In that planet there is intelligent life, and there they teach statistics, but they don't think that the probability is the fundamental object of statistics. They work with another variable, theta, and they propose that the relation between theta and the PD is cosine squared of theta gives us the PD. Because in Andromeda's galaxy, they like to express statistics in this way. As a consequence, they would say that the binomial distribution is the one that we see in the right. It's the function that we see in the right. It's the same function, and whenever we wrote PD in the left equation, in the right equation, we are writing cosine squared of theta. Okay, from our point of view, it looks pretty weird, but perhaps in Andromeda's galaxy, they study statistics in this terms. As a consequence, they would say that the fundamental object of study in statistics is not a PD, it's theta. And as a consequence, they would say that theta follows a uniform distribution. However, if they say in Andromeda's galaxy that theta follows a uniform distribution, they would find that the PD doesn't follow a uniform distribution. There is a formula that relates, okay, if theta has a uniform distribution, which is the distribution that inherits the PD parameter, given that the relation of the PD parameter and theta is cosine square of theta is the PD. However, we can see this result immediately by analyzing the graphic of this relation. Here we are seeing the graph of this equation, cosine squared of theta, where we have theta in the x-axis and the PD parameter cosine squared of theta in the y-axis. Here we are working with cosine squared of theta because we are working with a particular example. However, we in the Andromeda's galaxy can work with this example. In another galaxy can work with another function and whatever. This is just an example. So when theta takes low values, the PD parameter takes high values, and when theta takes high values, the PD parameter takes low value. So we can ask, which is the probability of finding a PD parameter, supposing that theta is uniform, which is the probability of finding a PD parameter between 0.9 and 1. Okay, the PD parameter should be in this range. So theta should be in this range. Should take values more or less between 0 and 0.3. Then we can say, okay, which is the probability of having a PD parameter between 0.5 and 0.3. 6. Okay, in order to find a probability of default between 0.5 and 0.6, the theta parameter should take values between more or less 0.7 and 0.8. So these are the values that should take the theta parameters in order to let the PD be in the range 0.5, 0.6. We have one square of range. However, if we want the PD to be in the range 0.9 to 1, the theta parameter would be in the range, in this range. We have 3 squares that represent the range of theta. So if theta is uniform, the PD parameter is not uniform because different 10% range scenarios have different probability of occurrence. So if we, in the planet Earth, say that the PD parameter is uniform, in Andromeda galaxy, they won't say that the PD parameter is uniform. So when we are saying that the PD parameter is uniform, what we are doing is we are putting our personal belief because we are imposing that the PD is a fundamental object of statistics, and we don't know. In order to solve this guy Sheffield in 1946 developed a methodology called Sheffield's prior. It has an abstract formulation. It calculates the determinant of the information matrix. And what we found is that the default probability could be distributed in this way that we find here. 1 over the square root of PD times 1 minus PD. And what Jeffrey also found is that in this example, the theta parameter, the one that is used in Andromeda's galaxy, the theta parameter is uniform. So in a way, Andromeda, the guys that study statistics in Andromeda's galaxy were right and we were wrong. It looks like the theta parameter is more fundamental than the PD parameter. What his definition of prior distribution obeys is that it is some kind of method of algorithm that assign to a parameterization of a problem a prior distribution. Okay, here in planet Earth, we like to work with this parameterization. Okay, this is the prior that we should use for this problem. Okay, in Andromeda's galaxy, we like to work with this parameterization as a binomial distribution. Okay, they should work with this prior distribution. And with this method, with this formula that assigns prior distribution to parameterization of the problem, what he's able to do is to assign distributions that are consistent among them. That is to say, the results obtained in planet Earth with this parameterization and these prior distributions are the same than the result obtained in Andromeda's galaxy with this parameterization of the problem and this prior distribution. So in a way, that is the way that Sheffie used to solve this problem. The other 1 minute more, Emiliano.
Yeah, yes, continue.
I told you that the uniform distribution had 2 problems. This was one of the problems. It depends on our personal beliefs. When we say that the PD is uniform, we are saying it because we think that it is the fundamental object of a statistic. And perhaps it is not. We can parameterize a statistic in different ways. However, we are not talking anything up to now regarding objectivity or agnosticism. We are just talking about consistency. Okay, is there a way of defining objectivity or let's say agnosticism? There are some ways. This view was taught by Bernardo. He invented what is called a method called reference prior, and he based on a previous work developed by Shannon. Shannon created what is called information theory. He quantified the amount of information involved in certain objects, for example, a statistical distribution. He also developed a measure of called mutual information, in which you can measure the information shared by two objects. For example, the information shared by two statistical distributions. And Bernardo took that mutual information and he said, okay, when we propose a distribution in order to weight the scenario that we were talking before, we should work with the distribution that maximizes the mutual information with the distribution of the problem, that binomial distribution that we were talking in the slide before. Why he said that? In a way, maximizing the mutual, inventing a distribution, a way that maximizes the mutual information with the distribution of my problem, implicitly, what it does is minimizing the subjective information that we are adding to the problem. If we are maximizing the information shared with the distribution of the problem, when we are inventing a weight, a third weight, a second weight, what we are doing implicitly is minimizing the information we are adding to the problem. And that is the better definition of objectivity / agnosticism. So there is a mathematical formula that performs this calculation. Doesn't mind at this point. What it is nice to see is that the statistical distribution that maximizes this mutual information with the distribution of our problem is exactly the same that the one obtained by Sheffield's method. That smile function defined by the formula we saw in the previous slide, 1 over the square root of PD times 1 minus PD, is the same distribution that we can obtain by this method. This method is harder in terms of mathematical computation, but at least for this simple problem of estimating one default probability, both methods, Sheffield's method and the Bernardo's method of reference prior, both reach to the same distribution in order to perform this other way. So this is more or less the idea of why weighting our scenarios by the one distribution is not agnostic and why there are better ways of weighting our scenarios. The answer was pretty long, but you asked difficult questions.
Thank you, Gus. It's really interesting this idea. You mentioned something about how this Sheffie probabilities or Geoffrey distributions are applied in order to calibrate a rating model, no, or in general to assign probability that should reflect some kind of order. Can you tell us more about that?
Yes, yes. This is once we present these ideas, we introduce these ideas in our paper. What we do is to apply these ideas in order to solve this calibration of rating model problem. Here we have a typical example. We have different categories: rating 1, rating 2, rating 3, rating 9. Rating 1 is the best category, the one that should have assigned the lowest default probability. Rating 9 is the worst category, the one that should have assigned the highest default probability. And in low default portfolio, typically we find that there is not a congruence between the economical sense and the statistical databases. In this example, for example, we see that the observed default rate is 1/20 for the best rating category, and it is 0% for the next two categories. So the observed default rates do not represent correctly the hierarchy of the rating category. Typically, what it is done in the practice in order to solve this problem is to fit these observed rates with a with an increasing curve. I cannot pronounce the word. Monotonically increasing.
It's okay. It's okay. We can understand the idea.
Okay. However, the functional form of this curve is chosen in general by subjective decision. Okay, let's work with an exponential. Let's work with a logarithm. Let's work with a polynomial. Whatever you choose, you will reach two different results. And this is a big problem because in some cases that can produce big changes in your economic calculations, in your economic capital measurements, in your expected losses measurement for credit risk allowance, in your loss reserve insurance actuarial calculation, wherever you're doing it. So what we said is, okay, let's try to find the Jeffrey prior of this problem. Can we apply the method developed by Jeffrey in order to solve this problem? If we are able to find this Jeffrey prior, okay, we can perform some kind of average among the different PD scenarios, and as a consequence, we would obtain an objective measurement of the PD curves that this statistical database is trying to tell us. The idea is to perform more or less the same calculation that we stated before, but having in mind that we have scenarios of ordered PDs. We have scenarios in this example 9 PDs. The PD of rating 1, the PD of rating 2, etc., the PD of rating 9. For each of these scenarios, each of the PD is ordered. The PD1 is lower than the PD2, the PD2 is lower than the PD3, and so on. And for each of these scenarios, we calculate two things. The likelihood of finding this statistical database, that is to say, this default given this trial, and given that PD scenario, that particular order PD scenario, and we also calculate the appropriate Jeffreys prior distribution, this Jeffreys weight, this Jeffreys second weight that should be applied to this problem. When we try to apply the method proposed by Jeffrey to this problem, we found that this is indeed possible. We found the Jeffrey prior that should be applied to this problem, and as a consequence, we were theoretically at least able to perform this calculation. Okay, we are going to grab each curve, each PD curve for each scenario, and each PD curve is going to be weighted by the corresponding likelihood of the statistical sample given this PD curve and with the Jeffrey period distribution given this PD curve. The problem that we found in our paper is that this 9-dimensional integral that we have to calculate can't be solved analytically. As a consequence, we have to measure it numerically. But when we try to calculate numerically this 9-dimensional integral, we find that it is not computationally viable, because if we want to discretize each integral in, for example, 1,000 steps, we have 9 integrals, so we have to perform 1,000 to the 9th power. That is to say, a 1 and 27 zeros of calculation. That can be done with a normal computer nowadays. So what we also developed is, what we also did is to study the Jeffreys prior of this problem, the Jeffreys prior of this problem, and propose a simulation method. So instead of discretizing this integral, what we did is simulate the PD curves that with the Monte Carlo simulation method coherent with the Jeffrey prior that we obtained. As a consequence, we transform this 9-dimensional integral in simply a sum. In this sum, what we have done is we have proposed, they were 1 billion PD curve scenario. This 1 billion PD curves scenario was simulated by a Monte Carlo simulation model coherent with the Jeffrey prior of this problem. And once we have for each scenario, PD curve, we weighted each PD curve with the likelihood of finding this statistical database, this amount of defaults in this trial, given the PDs of each of these scenarios. In this formula, omega represents each of these scenarios of the ordered PD curves, and here we have the weights related to the likelihood of finding 1 default in 20 trials, 0 defaults in 25 trials, 0 default in 20 trials, etc. It is just the product of the binomial calculation for each of these cells. And what we are doing is weighting each PD curve by this weight that represents the likelihood of finding the statistical data given the PD curve that we are working with. As we are working with a scenario that accommodate all of them to the order imposed by our analysis, the average we obtain, weighting each of these ordered PD scenarios, is also well ordered. And as a consequence, we have several examples in our paper. This is one of them. In this example, what we calculated is, okay, let's grab this statistical theoretic database. We have 100 exposure for the AAA notch, for the 100 exposure for the AA notch, and so on. And we have one default for the AAA notch, 0 default for the AA notch, and so on. So the naive default rate for the AAA notch is 1%, 1 over 100. The naive estimation of the AA notch of the default rate is 0%, 0 over 100. Okay, the one-dimensional based estimation, 0.5 over n plus 1. Okay, it has some kind of improvement theoretically when we compare to it, but obviously it does not represent also the order because it's just a one-dimensional calculation. It sees only the segment of data related to this category. For example, this calculation for the AA notch is 0.5, 0.5 over 100, and so on. But then we compare it with our 9-dimensional based Monte Carlo method. In this Monte Carlo method, we have proposed, as we mentioned, 1 billion PD curves. For each of the PD curves, we weighted them with the binomial likelihood of finding this default in this exposure, and we obtain, as a consequence, a well-ordered PD curve estimation. This is in a nutshell, or not so much in a nutshell, but as much as I could, the result we obtained in our paper.
Thank you, Gustavo. When you proposed me to write this paper with you, my first thought was, this is a revolution, and you show us that. In fact, this paper or this method has a lot of applications. Although we saw many formulas, no, I believe this is relatively simple to apply, and in the way that we don't need to use a neural network solution or a quantum computer. No, I don't know what is your opinion in that way, and maybe which is the effort of apply this kind of solution in a bank or in any industry.
Yes. No, it's not much effort. The first result, the 0.5 over n plus 1,
It's
really is easy as the naive estimation. So big improvement in comparison to what is usually done. I have to repeat, that is not our result. What we are doing is we are telling our audience, we are telling the financial quant community that this problem was already solved. Come on, use it in order to solve your credit risk measurement in low default portfolio. When we have to tackle the problem of calibrating a rating model, it is a computationally harder problem. It involves some kind of Python model and such, but yes, it is not a quantum computer, or whatever. However, yes, I have to mention, when we increase the number of categories. For example, when we are talking about estimating a mortality table, we have to estimate the mortality rate for each age. We have, I don't know, 18 mortality rates. We will have to rethink how to perform this calculation, because again, we will have statistical mistakes in the simulation of the mortality curve and such. So we have to be very careful in analyzing the curves we are simulating in order not to incur in statistical errors, because we are not working with the pure full parameter space, but we are working with just a couple of simulations. A billion simulation, but it is just a tiny part of the parameter space.
Okay, thank you, Gus. We are running out of time. I don't know if there is any other question. We have some minutes to answer. I don't know. Maybe the question will be in Spanish too.
Okay, if there are no more questions, well, thank you very much for participating in this lecture. Again, if you have any other question while you are reading our paper, please let us know. You have our emails, and we will help you with any question you might have.
Okay,
Thank you very much again.
Okay, and thank you to UCEMA to give us this space, no, to present it.
Thanks, UCEMA, for the space.
Thank you very much, Emiliano and Gustavo. It was a pleasure.
Thanks.
Thanks. Bye.
Bye.
Thank you. Bye.